In this section we're going to talk about fluids, and fluids encompass both gases and liquids in contrast to solids. And in this context we'll also discuss the important concept of the thermodynamic limit. So fluid, that can be a gas, or a liquid. In any case, it's different from a solid. And what's characteristic for a fluid is that its macroscopic properties are usually characterized by three variables. The macroscopic data are typically the volume, the particle number, and the internal energy. Now, there are different ways of incorporating these macroscopic data in your mathematical description. We talked in our general framework, we had talked about different types of macroscopic data. In particular, the distinction whether a certain value is given as a sharp constraint or whether it's given as an expectation value. So here we will generally have to distinguish three cases depending on which of these three variables is given as a sharp value and which is given as an expectation value. In the first scenario, all three variables are given as sharp values, and none of them is given as an expectation value. In that case, the macrostate that you construct is called microcanonical. One sometimes speaks also of an ensemble rather than a macrostate. So this is the microcanonical case. When is this relevant? This is relevant when you have a perfectly isolated system, where you don't have any exchange of particles, of energy with an environment, and hence particle number, energy are strictly conserved, and if you are also able to control their values within some measurement uncertainty, which is always there, then the appropriate ensemble or macrostate would be the microcanonical macrostate. A second case is the case where the volume and the particle number are given as sharp values, but the energy is given only as an expectation value. This is a case that we've already encountered in various examples, and the macrostate that describes such a situation, such a system, is the canonical state. It's the Boltzmann-Gibbs state, where the Hamiltonian features in the exponent of your density matrix, because the energy is the only observable that is given in the form of an expectation value, and volume, particle number are fixed. When is this the appropriate choice? This is the appropriate choice when you have no exchange of particles, so the particle number is fixed, but you can exchange energy, say in the form of heat, with the outside world. And finally, there is the case where only the volume is given as a sharp constraint. The volume is always given as a sharp constraint. The volume is an external control parameter, so the volume is never given as an expectation value. That's always a control parameter with a sharp value. In this last case, then the volume is the only such sharp value, and both the particle number and the energy are given as expectation values. The associated macrostate or ensemble is then called grand canonical. And when is this appropriate? In the same logic, when you have exchange of both particles and energy. These are the classic ensembles of thermodynamics. So these three types: microcanonical, canonical, and grand canonical. A key result of our discussion will be that in the thermodynamic limit, and we will have to specify what exactly we mean by the thermodynamic limit. In the thermodynamic limit, in fact, it doesn't matter which of these three ensembles you use to describe a system. So even though I listed them as distinct ensembles, distinct cases, when you are in the thermodynamic limit, and up to the description of fluctuations, they give different predictions for the size of fluctuations. But as long as you are not interested in fluctuations and you are interested in all other thermodynamic properties, it will turn out that in the thermodynamic limit, in fact, it doesn't matter which of these three macrostates you use. But for the time being, and it's important to keep in mind that there is this distinction. Let's now talk about the various aspects of the thermodynamic limit. And the first important aspect is the idea of homogeneity. What's the basic idea behind homogeneity? It says when you have a large system and I take a sample of this system, I have, say, a gas or liquid in a large container, and I take a small sample, and I can investigate the thermodynamic properties of this sample. Say the equation of state, the heat capacity, other thermodynamic properties of this sample that I take. Then homogeneity physically says that I will find the same thermodynamic properties no matter where I take the sample, which shape my sample has, and what size my sample has. So take the air in this lecture hall, in this lecture room, and I want to investigate the thermodynamic properties of the air, and I can go to the right corner of the room and take a little probe, a little sample, or I can go to the left corner of the room, take another sample. I can take, in the first case, I can take a liter. In the second case, I can take 3 liters. And my bottles may have different shapes. But in all cases, I will find the same thermodynamic properties of the air. And it also means that I can, when I have a homogeneous system and I take a probe and investigate the thermodynamic properties, then what I learn from that probe, I can extrapolate to the entire system. So if I take my probe of the air in this room and I investigate, I don't know, the relationship between pressure, volume, and temperature, and compressibility, heat capacity, whatever you want, of that probe, then I can extrapolate and I can say, this is valid for the entire air in this room. And in fact, it's a very fundamental requirement that enables you to, in a certain way, it's something very basic that enables you to do science at all. Because when you do science in the laboratory, you want to learn, ultimately you want to learn something about the world around you, but you can never investigate the entire world. You always take samples and you investigate them in the laboratory, and then you want to be able to extrapolate what you found in the laboratory to the world outside. So this very much relies on this idea of homogeneity. So let me write down in a few sentences what I just said. The basic idea is that you find the same thermodynamic properties regardless of where I take a sample and regardless of the size of the sample and the shape of the sample. So I have the entire system here. As I said, this might be the air in this room, and then I might take a probe here, probe or sample number 1, and I might take another sample here with a very funny shape. Let's say this is sample number 2, and here I might have a tiny sample number 3. Whatever sample I take and where I take it, I will find the same thermodynamic properties. And as I said, this is an extremely important property that in a certain way enables us to do science at all, because then what you can do is you can study samples of a homogeneous system in the laboratory. You can learn about their thermodynamic properties, and then you extrapolate your findings to the entire system. So this is the basic physical idea behind homogeneity. The next question is how you formulate this mathematically. What is the mathematical criterion for homogeneity? What does it mean to say that two samples have the same thermodynamic properties? We said earlier in our general framework that either the log of the partition function as a function of its natural variables, so the Lagrange parameters and the control parameters, that this log of the partition function and the functional dependence on its natural variables encodes all the thermodynamic properties of a system. And likewise, alternative representation is the entropy as a function of its natural variables. In this case, this would be energy, particle number, and volume. And the functional dependence of the energy on its natural variables encodes all thermodynamic properties of the system. And from that function, you can derive, by taking partial derivatives of first order, second order, you can derive all thermodynamic properties of the system. So when we say that two probes have the same thermodynamic properties, then mathematically this means that for both probes we have the same functional dependence of entropy on its natural variables. That's a starting point. Let's look again at the entire system. And let's say the entire system has volume V. And now we take from this entire system, we take a sample, and the sample has volume x times V. And x, little x, is a fraction. It's a number between 0 and 1. So we take the sample is a fraction, x, of the entire system. Now, homogeneity means, or we say, if the sample has volume x times V, then it also should have a fraction x of the particles. So it should have particle number x times n. It should also have a fraction x of the total energy, x times u. And if we require that the sample exhibit the same thermodynamic properties as the entire system, then we must demand that it also has a fraction x of the entropy. So in addition, we demand that it also has a fraction x of the entropy. Now the entropy is of the sample. The entropy of the sample is given by, is a function of the volume, particle number, and energy of the sample. Now energy, particle number, and volume of the sample are fractions x of the entire system, respectively. And then the entropy of the sample is this function s of x times u, x times n, and x times v. And this must be equal to, that's what we required in red, that the entropy of the sample is also a fraction x of the entropy of the entire system. So this must be x times the entropy of the entire system, which is a function of the energy, particle number, and volume of the entire system. So this is the mathematical criterion for homogeneity, that we say volume, particle number, energy, and also entropy of a sample when I take a fraction x of the entire system. All these quantities must be fractions x of the entire system, and the same functional relationship must hold between energy, entropy and its natural variables u, n, and v. So the equation inside the box must hold. This is a very fundamental point here, and we will spend some time deriving consequences of this homogeneity requirement. So it's important for me that you understand this starting point. Before we look at the consequences of homogeneity, let's think of a counterexample. Let's think of a system that is not homogeneous. Well, homogeneity is violated whenever you have surface effects that are non-negligible. And an example from everyday life that you all know are little water droplets. And you have, the very fact that you have water droplets is a consequence of surface tension of water. So you have non-negligible surface effects. And this makes them not homogeneous. And this means if I have a big water droplet with a given energy, particle number, and volume, and then I split this big water droplet into two small water droplets, where the two small water droplets have each half the particle number, half the volume, and half the energy of the big water droplet, then their entropy, or the sum of the entropies of the two small water droplets, will not be equal to the entropy of the big water droplet. And that is due to the surface effects. Maybe another way to see it, you could invert the equation. You can look at the energy as a function of entropy, particle number, and volume. you can say when I insulate the system so I don't have any heat flows between the water droplet and its environment, then I have no heat exchange, then the entropy should be conserved. We'll talk about that later when we talk about thermodynamic processes, the various criteria for conservation of entropy and so on. But you can say that you can split the big water droplet into two halves in a way such that there's no heat flow and therefore no change of total entropy. Yeah, so let's suppose you can do that. So you could split the big droplet into two small droplets without a change in total entropy. So each of the two water droplets should then have half the total entropy, half the particle number, and half the volume of the original big water droplet. But due to the surface tension, you have to perform mechanical work to separate the two halves. And for this reason, the energy of a small water droplet will not be half the energy of the big water droplet. Or in other words, the total energy of the two small droplets will be different from the internal energy of the big water droplet, because in the process of splitting the big droplet into two, you had to perform mechanical work. So you had to add energy to the system, and this increases the total internal energy of the system. Another way of phrasing homogeneity is that you can say a system becomes or is homogeneous as soon as surface effects become negligible. So while in the case of a small water droplet, surface effects are not negligible, if I take an ocean, so a huge quantity of water, then, and I want to describe, I don't know, the hydrodynamics of the ocean, then I can, with good approximation, neglect surface effects, because the ratio of surface to volume is much smaller when I have a large quantity of water than if I only have a droplet. Okay, after this counterexample, let's come back to the case where the system is homogeneous, and let's look at some consequences. One consequence is that you can make a distinction, a clear distinction between thermodynamic variables that are extensive and others that are intensive. What do extensive and intensive mean? A quantity is called extensive when it is additive, when I put together, when I put systems together. So I have two systems A and B. The first system has particle number N1. The second system has particle number N2. It's the same type of particles. I put them together into a single system, and then the total system will have particle number N1 plus N2. So the particle number is an obvious candidate for an extensive quantity. It's additive when I put systems together. In the picture that we had on the previous page, where we took a fraction x of a big system as a sample, then we can say a quantity is is extensive if it scales with x when I take a sample. So an alternative formulation is that an extensive quantity or extensive quantities scale with the fraction x when I extract a probe or a sample. Now, examples for extensive quantities. One example I already mentioned, the particle number. Also, the volume is extensive. The internal energy is extensive. And if the system is homogeneous, then in addition, also the entropy is extensive. And there are more. For example, the total magnetic moment of a system and others are also extensive. In contrast to extensive quantities, there are intensive quantities, and they are characterized by the property that they are invariant when I subdivide a system. Or equivalently, in our picture of where we take a fraction x of an entire system as a probe, then an intensive quantity will have the same value for the probe as for the entire system. So it's the same when I take a probe. What are examples here? The temperature, the pressure, the chemical potential. In fact, all conjugates of the natural variables of the entropy. Yeah? So in fact, all conjugates of the natural variables, which in this case are u, n, and v, with respect to the entropy. For example, let's look at the inverse temperature, beta. Let's look at the inverse temperature of the entire system. How do I obtain that from the entropy? I take the partial derivative with respect to the conjugate of beta, which is the internal energy U. It doesn't matter if I insert in both in the numerator and the numerator and the denominator a factor x, which characterizes the fraction of the probe. I can simply insert the x there. Then since the system is homogeneous, I know, that's my mathematical criterion for homogeneity, that x times the entropy, which is a function of u and v, is the same as the entropy S as a function of x times u, x times n, and x times v. So I can also write that here as instead of x times s, I can write s as a function of x times u, x times n, and x times v. And I also have the divided by k over x times u. But now what I have on the right-hand side, this is the inverse temperature of the probe, because the thermodynamic properties of the probe are characterized by the entropy function S as a function of x times u, x times n, x times v, and the probe has in particular has the internal energy x times u. When I take the partial derivative of this entropy function with respect to x times u, so with respect to the energy of the probe, then I get the variable that is conjugate to the energy of the probe, and that is the inverse temperature of the probe. So this gives me beta x, the inverse temperature of the probe. So you see that indeed, due to homogeneity, which entered here, due to homogeneity, the inverse temperature of the entire system equals the inverse temperature of the probe. And regardless of where I take the probe, what fraction x of the system I take as a probe, you always get the same inverse temperature. Well, if the inverse temperature is intensive, then of course the temperature itself is also intensive. And you can use the same logic, the same derivation to show that also the pressure and the chemical potential are intensive quantities. But it's important to realize that you have this clear distinction between extensive and intensive only if the system is homogeneous. If it is not, then there's no clear, in general, there are then variables that cannot be uniquely classified as either extensive or intensive. The examples that we have seen so far for extensive quantities, particle number, volume, energy, and so on, were rather obvious. I'd like to argue here that if you have a homogeneous system, then the partition function, and more strictly speaking, more precisely, the log of the partition function, is also an extensive quantity. And I would like to look at the partition function of the grand canonical ensemble. So you remember the three cases that we have to carefully distinguish, at least up to this point, where we haven't shown the equivalence yet. The three cases with the three different ensembles. I would like to work here with the grand canonical case. So both energy and particle number are given as expectation values. Then the associated partition function, the grand canonical partition function, is given by the trace of e to the minus beta h, as in the canonical case. But then we have, in addition, we have the particle number given as an expectation value, so the particle number operator also features in the exponent, the observable for particle number. And we said the associated Lagrange parameter is minus alpha. So this gives us then effectively a plus alpha, and this is the observable of particle number. Now, in the grand canonical case too, we can use the relationships that we can infer from the Guggenheim square. In this grand canonical case, this implies that the log of the grand canonical partition function is related to the entropy by, first of all, subtracting beta times u, as in the canonical case. But then in addition, since we are here grand canonical, in addition, we have to add alpha times n. The n without the hat is the expectation value of particle number. It's the same logic as before. What we used recently was, in the canonical case, we used that entropy is equal to a log of the partition function plus beta times u. If you solve that for the log of the partition function, you get This is equal to entropy over K minus beta times U. And now if you have additional expectation values with associated Lagrange parameters, then the general rule that's encoded in the Guggenheim square tells us then we have to subtract from the entropy also the other products of Lagrange parameter times associated expectation value. In this case, the Lagrange parameter is minus alpha. The expectation value is n. Subtracting that means effectively adding alpha times n. I can also just quickly show you, just to remind you, the general framework. Here it is. We had in the first line, we had a general formula for the entropy, relating it to the log of the partition function and the products of expectation values with associated Lagrange parameters. When you solve that for the log of the partition function, then you find it's entropy minus sum over I, Lagrange parameter lambda I times expectation value. In our case, in the grand canonical case, we have two expectation values, U and N, and the associated Lagrange parameters beta and minus alpha. And this gives rise to the formula that I just showed you for the log of the partition function, the grand canonical partition function. Let's now study the right-hand side and investigate the various variables that appear there under the aspect of extensivity versus intensivity. The entropy we found is an extensive quantity if the system is homogeneous. The internal energy is also extensive, and the particle number is extensive. The inverse temperature, in contrast, is intensive, and so is the Lagrange parameter conjugate to the particle number alpha. This alpha is also intensive, in the same logic as for the beta. When you multiply an intensive quantity with an extensive quantity, you get an extensive quantity. Why is that? Take from the entire system, take a probe, a fraction x. Now, the probe has energy, say, x times u, and it has the same inverse temperature, beta. So the product beta times u for the, so beta time inverse temperature times internal energy for the probe is x times beta times u. So it's a fraction x of the product beta times u for the entire system. And likewise, here the product alpha times n is extensive. So we find that the log of the grand canonical partition function is an extensive quantity, namely the entropy, minus beta times u, which is extensive, plus alpha times n, which is extensive. And of course, when you add up extensive quantities, the sum of extensive quantities is also extensive. So as a consequence, we find that the log of the partition function is extensive too. What does that imply? Let's look at the log of the grand canonical partition function for the probe. Now, the grand canonical partition function has as its natural variables the two Lagrange parameters, beta and alpha, and the volume, which is an external control parameter. So these are the natural variables of the grand canonical partition function. When you look at a probe, so you take a fraction x of your total system, then you have only a fraction x of the volume, but you have the same alpha and beta because these are intensive variables. So this is the log of the partition function for a probe. Being extensive means that the log of the partition function for the probe must scale with x. So it must be a fraction x of the log of the partition function for the entire system. Here on the right, this is the log of the partition function for the entire system. And on the left-hand side, we have the log of the partition function for the probe. And as I said, being extensive, this must be a fraction x of the log of the partition function for the entire system. Now, keeping alpha and beta fixed, the log of the partition function of x times v equals x times the log of the partition function of v. This implies that the log of the partition function must be linear in v. So this implies that the log of the partition function, the grand canonical partition function, must be proportional to v. And the proportionality factor must be the partial derivative of the log of the grand canonical partition function with respect to v at fixed beta and alpha, where this partial derivative then must no longer depend on the volume, must be independent of the volume. What is this partial derivative? It's the partial derivative of the log of the partition function with respect to the external control parameter v. We know from our general framework the v is an instance of this control parameter psi. So the v is on the top side of the square instead of the psi, and in the place of the psi. The Guggenheim square tells us that the partial derivative of the log of the partition function with respect to a control parameter psi, which in this case is the volume v, is the same as the partial derivative of the entropy with respect to v. In either case, you have to keep the respective other natural variables fixed. In the case of log z, you have to keep the Lagrange parameters fixed, the lambdas, which in our case are alpha and beta. In the case of the entropy, you have to keep its other natural variables fixed, which here are the particle number and the energy. And what is the partial derivative of the entropy with respect to v? This is we learn from this table, this is beta times the pressure. So in fact, we can say that this partial derivative in front of the v is actually equal to beta times the pressure times v. So this comes from the Guggenheim square, which first of all tells us that the partial of the log of z with respect to v is the same as the partial of the entropy with respect to v. This is the part that we learned from Guggenheim. And then from our table of conjugate pairs, we learn that the partial of the entropy with respect to volume is equal to beta times the pressure. So this is the second input here, the table of conjugate pairs with respect to entropy. With this line, in this line of reasoning, we obtain a very fundamental equation for the log of the grand canonical partition function, which holds for arbitrary homogeneous fluids that are characterized by n, v, and u, namely that the log of the grand canonical partition function is equal to beta times pressure times volume. Then we come to another important consequence of homogeneity, and this is the so-called Gibbs-Duhem relation. And it's going to be, for today, the final conclusion that we're going to draw from homogeneity. And the starting point is, once again, the relationship between the log of the grand canonical partition function and the entropy. And this time, I write it in the form I solve it for the entropy. This equals the log of the grand canonical partition function plus beta times u minus alpha times n. And then we can use the result from the previous page. We can say the log of the grand canonical partition function is beta times the pressure times volume. What remains is the beta u minus alpha n, where the alpha I would now like to write as beta times the chemical potential times n. This we can solve for the internal energy. And we find for the internal energy that this is given by temperature times entropy minus pressure times volume plus chemical potential times particle number. Then we can take the total differential of energy, du, and by product rule, we get TdS plus SdT and so on. I would like to group the various terms in a particular way. I would first like to write TdS plus SdT. Then I have minus P dV minus V dP. And then I have plus mu dN plus n d mu. The reason why I grouped it in this way was that in the first three terms I have differentials of extensive quantities, whereas the last three terms are differentials, they contain differentials of intensive quantities. So the T, P, and mu, they are all intensive. Do you recognize the first three terms, TdS minus PdV plus mu dN? We had seen this before. This is the differential of energy. This is du. Remember our discussion in the general framework where we looked at, we formulated this more generally, we looked at the differential of the energy, we looked at du, and we found that this du is TdS plus, and then depending on the other variables that we have then some coefficient times dx. and we had a table of the coefficients, and the coefficients were next to the temperature were the chemical potential and minus the pressure. So we didn't have this, didn't write this differential explicitly, but it's contained in this more general formula and in this table that in the case of a fluid, the differential of internal energy is given by TdS minus PdV plus mu dN. This is du. Well, if the first three terms already are du, and on the left-hand side we also have du, then this implies that the remaining three terms must add up to 0. And this fact, this equation, S dt minus VdP plus N d mu is equal to 0, this is the so-called Gibbs-Duhem relation. And it holds, as always, for homogeneous systems only. Now this has an interesting implication because it means that the three differentials dt, dp, and d mu are not linearly independent. So the intensive, and these are the three intensive variables of the system, thermodynamic variables of the system, and the Gibbs-Duhem relation tells me that these three intensive variables are not independent. So you can always express one of these three intensive variables as a function of the other two. Another consequence of that is that if you want to characterize a homogeneous system, the macrostate of a homogeneous system, it's not enough to characterize it only by intensive variables. It's not enough to say the air in this room has temperature 20 degrees and a certain pressure. That's not enough because it doesn't give you any information about the volume of the air or the particle number in the air. Yeah? So in order to characterize the macrostate of a homogeneous system, you always have to provide at least one extensive variable. It's not enough to characterize it with intensive variables. So this is the very basic, very fundamental Gibbs-Duhem relation and the physical implication of it.